I'm Sarah Lerch. I'm a postdoctoral researcher at Chalmers University of Technology.
And my name is Kasper Moth-Poulsen. I'm a professor here at Applied Chemistry at Chalmers.
And we are here to present our HSB Minihouse project, in which we use to look at molecular solar thermal energy storage materials, or MOST materials. So Kasper, why are we looking at MOST materials?
Yes, so before we come to the MOST materials, let me tell you a little bit about energy. If you look at what we are using the energy for in the EU, then 50% of our energy consumption is used for heating and cooling. The other half is split between power production and transportation. But if we look into the heating and cooling, a lot of that energy is coming from burning of fossil fuels. That is wood, oil, and coal. And when we burn that, we create emissions that are creating air pollution and also CO2 emissions that contributes to global warming. So when we started our research project, we wanted to develop a new type of energy system that could operate without any emissions. And that is the basic motivation behind our molecular solar thermal systems.
So what exactly is a molecular solar thermal system?
Yes, so this is a molecule. It's based on a molecule. Let's call it molecule A. It can capture sunlight. And when it's capturing the sunlight, it's absorbing the sunlight, it's converted into molecule B. This molecule B holds the energy as chemical energy, and then later, on demand, it releases the energy as heat and recovers the original molecule. So it's a closed cycle where the input is sunlight onto the molecule A, convert into molecule B, and then later we release the heat and recover A. So this is a cycle that we can operate for hundreds of thousands of times without losing any material and without creating any emissions. So it's a closed cycle energy system.
Are there a lot of molecules that are capable of this photo switching?
Yes, so today several research groups around the world are trying to develop molecular systems that can do this. There exist molecules called atobenzines, ruthenium fulvarenes, and also the Boron Dying Quadricycline photo switch system, which we have chosen to work on.
Why did you choose Boron Dying Quadricycline for the research?
Yeah, so Boron Dying is originally a natural product extracted from a plant in Borneo. That's why it's called Boron Dying. It has it's based only on carbon and hydrogen. This means that we envision that we can make this from renewable feedstocks from carbon and hydrogen only, and it's very easy to tailor its function. It has these two double bonds in a non-bonded form that absorb sunlight, and that is then converted into the quadricyclane, where you have four cyclic alkanes linked together, and that linking together is a lot of energy, strain energy, that we release when we convert back to the non-bonded. And what we are then doing is that the non-bonded as itself is only absorbing UV light, and it stores the energy for many, many years. What we need to do is to modify the functions so that it can capture sunlight, it can release the energy more easily, especially for the HSB Minihouse project here. We would like it to release the energy on a 4 to 8 hour time scale. But that we will come back to later. Yeah.
So what are some of the requirements other than the energy storage that you have for a successful MOST system?
Yes, of course. So it's an energy storage system. So we would like to store a lot of energy in a very little space. And these systems can capture and store up to 1 megajoule per kilogram. This is the same or above state-of-the-art lithium-ion batteries. Further, they are transparent. This means that they can be integrated into materials or applications where transparency is needed. This is very unique for energy storage technology to have something that is transparent. Further, they can be engineered to store energy for shorter or longer periods of time, and we can also engineer the colors. So altogether, we think that with this material we can have a very efficient energy storage system. We can capture the colors of the sunlight that we want, and we can tune how long time we want to store the energy for.
So how are you able to change the properties or the parameters of these materials to adjust for what you want to get with these energy storage?
So what we are doing is that we have the molecule, and then we are changing different components to better match the solar spectrum. So what we have is the molecule, but then we add so-called donor and acceptor systems. And by doing that, we change the solar light absorption, but we also change the energy storage lifetime, as we call it, the time it takes from the molecule is absorbing the energy till it's releasing the energy later on. So all these are something that we have learned how to engineer during our experiments in the chemistry lab during the last 10 years or so.
Okay. And now, how are you envisioning these most materials to be used in something like the HSB Minihouse?
Yes. So this then we have to tell a little bit of a story again, because if you look into what we really want from a house, or what we want to, I mean, we all like to be out in the great outdoors and experience the open air. But here in Sweden, some parts of the year this will be too cold, or during the nighttime it will be too cold, or some sunny days it might even be too hot. So that's why we build houses. So we build houses to shield ourselves from the elements, but also we would like to look out to the outside world through our windows. And here comes the problem. I mean, we have the sun. It's a very powerful source of energy. During the day, we get so much heat and light from the sun, and during the night, not so much. During the summertime, we get a lot of energy. During the wintertime, not so much. So I think most of us have experienced a hot summer day where the office got overheated because of too much energy coming through the window, or a cold winter evening where too much cold air came down through the window. So through hundreds of years, engineers have tried to build better windows or make solutions that mitigate these challenges by making windows that are very insulating, by placing radiators under the windows. And we thought that with our MOST system, we could maybe create a new class of windows where the variable output of the sun is used or mitigated by storing energy during the day, so less heating during the day, and then releasing the energy during the nighttime so that we get less cooling effect during the night. And if we are successful with this, then we will be able to create an entirely new window concept that maybe even change how we can design houses and live in the future.
Great. Can you talk about, like, what were some of your initial goals for this project?
Yeah, so we've been working with molecules in the chemistry laboratory for more than 10 years, and we can, of course, we love to do our job to work in the chemistry lab, but if this should really make a change in the world, we have to take it out and start to think about what we can do with it and try to demonstrate things. So that was why we started to do this project, and simply because we wanted to demonstrate a basic function of the system under more realistic conditions. So that was why we designed the mini house. So maybe I should ask you, Sarah, that you are actually working on this project and working on the house. What are the goals of the project, and how has they developed over time?
So as you said, our first goal is to make a sort of a real world application of putting these into a house. And one of the things that we noticed fairly early on is that, well, windows are usually pretty large, and our molecule, we can only make a couple of grams at a time, at least, in initial testing phases. And so we needed to have a system where we can use, small amounts of molecule. And so we came up with the idea where we can have these small windows on this mini house where we can put our molecule. Additionally, what we've learned as I've been working with this is that there are a lot of different aspects you have to consider when you're looking at window technology, and there's a whole industry related to how to build the most efficient and the most insulating windows. And so what we had to do initially was start figuring out, how does our mini house model those windows, and what's the best method in order to have the highest effect, where we put our material, how to, how does that change with a smaller window or a larger window. And so we've sort of shifted a little bit back to looking at sort of the basics of window technology in this house and where our material is actually the most useful, and some other components of windows that are commonly used.
Great. So how are you actually testing the most materials in the mini house?
So what we are doing right now is we can make a film or a panel of our material that is incorporated into a polymer. So we mix the molecules in with a polymer, we then dry it out, and we can create either a film or a material through pressing that under heat. So it's called hot pressing. And then what we can do is we can put that material into the windows, and we can put them into just as their own by themselves as a panel, or we can put them into a more traditional window construction where you might have 2 or 3 panels of glass or plexiglass, depending on the system. And so then we can see where in this system our molecular panel works best.
Okay, cool. So what kind of measurements are you then doing on the mini house?
So predominantly we're measuring the temperature and the heat flux. And those can actually give us some insight into insulation values, which is important if we want to take into account the absorption, helping to keep the house cool by absorbing some of that sunlight in the beginning of the day, and then releasing that heat in the evening in order to, heat the house back up after, it starts to cool down outside. So we measure the temperature inside the house and outside the house, and then we can also measure the temperature at various points within the windows, even within the panes themselves if we try to, but especially between different panes of windows. And that allows us to see what the temperature difference is across the window. We can also monitor the heat flow or heat flux across any individual pane to see when we can see that heat release, or perhaps more, in most of our systems, we see less than a heat release and more that the heat does not change as much when we have that material, because it actually provides a lot of insulation by absorbing both the sunlight and then also releasing the heat, which keeps the cold sort of out of your material.
So what kind of measurements can you do with this mini house that you couldn't do before in the lab setting?
So we actually do a lot of the same measurements that we do in a lab setting. We're just doing them on a larger scale, which eliminates some problems that we had in the lab setting. For example, we had something that we saw which was called edge effects, which is if you've ever been in a room with lots of windows, right around the edges where the windows connect to the walls gets a little bit cold because there's sometimes there's air gaps there where the air can seep through from the outside, and it's very hard to insulate those effectively. And even if you do insulate them effectively, it's a different insulation than in the middle of the window pane, and that can be very hard to replicate on a small scale. But once you have larger windows in this mini house, we start to see the effects, especially if we go right to the center of the pane rather than on the outsides.
So in order to visualize this energy absorption and heat release, we have made a colored film that can sort of illustrate what we are talking about. The future window might not be colored, but this first generation thing is also made to visualize what is happening. Can you tell us a little bit about the demonstration that we are seeing now?
Yes, so we actually have 2 window panes. We have one that is sort of a bright orangish yellow color, and that one actually changes very quickly. It absorbs the energy and goes towards transparent, and then in about half an hour or 40 minutes, it will change back to orange once you block the sunlight from coming into the system. And the other panel is a lighter yellow. It's more closer to only absorbing in the UV, and that takes a much longer time period in order to change back. It absorbs more energy, it releases a little bit more energy than the orange pane, although it releases it over a much longer time, so it's a little different when you're looking at the actual measurements themselves.
So thank you very much, Sarah. Thank you for listening in. We will continue to do our research, and hopefully we will be able to show real-world windows in the coming years with this new exciting technology. So thank you for listening in.